Well, good afternoon, or if you're in my time zone, good morning. As Avarangui said, I'm Denise Levitan from the United States Geological Survey, and I'm going to talk about some work that I've recently done with my colleagues here, Alan Kolker, Brett Valentine, and Ryan McAleer, who at least some of them are on this call, so good morning to you guys. And quick disclaimer before I start, preliminary data, U.S. government and U.S. Geological Survey, not liable. So just a quick intro before I start to who I am, who we are. The USGS is a government agency within the United States Department of the Interior. Our South African analog would be the Council for Geosciences. And we study natural systems, natural resources, natural hazards, shown by our 5 mission areas listed there on the right of this slide. And we're a scientific agency. We don't have regulatory authority, and we don't create government policy. We just look at the science. So USGS has studied coal within the United States and globally throughout our history, and even before we were formed. Our precursor surveys, you can see a drawing of down in the bottom. I've looked at coal over the 3 centuries. We've mapped where coal is, assessed how much there is, looked at what the properties of it are. And then we have maps, research reports, and data available for public use that you can get on our websites or in various scientific journals. And then today, there's me. I've been with USGS as a research geologist for the past 3 years. I focus on the inorganic geochemistry of coal. And before I came here 3 years ago, I did work as an environmental and natural resources consultant. And that does inform some of what I'm going to talk about. So before I really get into it, just some common terms so we're all on the same page. So in the title, I used rare earth elements in coal ash. And coal ash, it can be fly ash, which are small particles that leave the coal boiler with gases, or bottom ash, which is material that settles to the bottom. But I'm going to call coal ash throughout this presentation CCR, or coal combustion residuals. That's the term that's more commonly used in groundwater quality regulation and compliance. And like I said, that's what I worked in. So it's a convenient term to distinguish from the property of coal, some that I'm going to talk about some also, which is ash yield or ash content. And that's the fraction of the coal that consists of non-volatile mineral matter, which I'm going to get into more. And you can see in that little diagram the different fractions of coal and where ash fits in. So the reason that we're interested in CCR, at least in what I'm going to talk about today, is that it can be a source for critical minerals, especially rare earth elements. If we deplete the reserves we have or have difficulty accessing traditional deposits, because there are still some economic aspects to work out of the extraction process, which is important, but beyond the scope of what I'm really going to talk about today. So CCR is formed when coal is combusted. And when that happens, as you probably know, most of the coal is transformed into gases like carbon dioxide. But not everything in coal is combustible. And so a lot of the material, or some of the material, remain in a solid. And that's what CCR is. That ash content becomes leftover residual in the bottom, or in baghouses or electrostatic precipitators designed to collect fly ash. But not all of the elements within coal behave the same during combustion. So like I said, carbon and sulfur get oxidized into dioxide gases largely, and they go out the stack or into the emissions controls. But rare earth elements, they don't volatilize. And so they remain in that solid in the CCR. And you end up having the same mass of rare earth elements, but you have a smaller total mass in the residual relative to the original coal. So because you have that same total mass dispersed within a smaller total mass, you get an increase in concentrations of rare earth elements relative to your original coal. And you can kind of see that in the plot there with CCR being blue, and you can see it's higher than that green coal. And in a lot of cases, not only are the rare earth elements in CCR enriched relative to the original coal, but also relative to other geologic materials like the upper continental crust, which is one on that plot there. So sometimes CCR is used or reused in construction as a supplementary cementitious material, or as fill or some other applications. But a lot of times in a lot of places, it's considered a waste product and a potential environmental liability. In my past, I looked at how potentially toxic elements could leach out of CCR and into groundwater, which then could become a big environmental concern. So processing CCR as a feedstock for critical minerals can be another type of beneficial reuse beyond those construction applications. Another advantage to CCR relative to, say, mining rare earth elements is that it's already been dug out during the original coal mining. It's been brought up to the surface, crushed into small particles, so it doesn't require a lot of the same effort, energy consumption, big holes in the ground, or additional big holes in the ground that mining a traditional rare earth element deposit might require. So like I said, CCR is a product of coal combustion. It's there in the name, which is mainly done for electric power generation. And that process occurs within boilers at coal-fired power plants. So there's two general technologies that are used in modern coal-fired plants. I'll be a little simplified, so if you're a plant engineer, don't get too mad at me. But we have pulverized coal-fired power plants. They're the most common. And then there's circulating fluidized bed reactors, which are less common, but still existent. And some of that is because pulverized coal-fired or PCF plants, they're more established technology. They generally operate a little bit more efficiently than CFB plants, which started coming online during the 1980s. The range of coal types or coal and other fuel types that can be burned in a CFB plant is more diverse than in a PCF plant. But a PCF plant also requires additional systems for controlling sulfur dioxide and NOx emissions. So in places where your available coal might have a lower volatile content or a higher ash content, or where you don't have as much space for some of those emission control structures, CFB plant might be preferable. And like I said, if you're an engineer, there's a lot of differences in the designs. I just have these pretty basic schematics as illustrations here. But if you're a geochemist, the two big differences between a CFB plant and a PCF is that the CFB plants burn at a lower temperature, a few hundred degrees Celsius lower, and that CFB plants a lot of times will have limestone or sand added into the mix to keep that fluidized suspension going. So today, surprise, we're going to Vietnam. I'm going to present a case study comparing CCR from a couple different plants in Vietnam. And this work is based on samples that were collected by my colleague, Dr. Allen, while he was serving as an embassy science fellow at the U.S. Embassy to Vietnam in Hanoi in 2023. And while he was there, he worked with both the Vietnam Institute of Geosciences and Mineral Resources, or Vietnam's USGS, and the Korea Institute of Geoscience and Mineral Resources, or South Korea's USGS. So I want to acknowledge the work that all of those agencies did in helping us with this project. So a little background on Vietnam and coal. They get about a little under half of their electricity is generated from coal. And coal-fired power plants there produce around 25 million tons of CCR each year. So they have a lot of it. Vietnam has an established coal mining industry, and they produce about half of the coal that they use. So the other half is imported. And Daniel, you have your hand raised. Can you hear me okay or see the slides?
Yeah, sorry. Everything's good. Sorry.
Okay, great. Yeah, they import about half and produce about half domestically. And pretty much all the coal that they mine is anthracite or semi-anthracite in some cases. So it's high-grade coal, but it also has a really high ash yield, sometimes greater than 30%. For some context, in the US, most of the thermal coal that we produce is below 10%, and our Western subbituminous coal is usually less than 5%. From what I'm told, in South Africa, it tends to be like in the 20s. So more than 30% is a pretty high value. The largest coal mines in Vietnam are in the Cam Pha coal field, which you can see on this map. It's in the Quang Ninh province in the northeast. The coal field itself geologically is in the pink area on the bottom map, which is an upper Triassic unit. And that star shows the general location of some of the largest mines that I'm going to talk about. So just a few kilometers from those mines, there's these two neighboring coal-fired power stations at Mong Duong, which I'm going to call MD. So on the map, you can see in that orange oval, I've circled some of the surface workings of the mines. A lot of them also go underground. They have really strongly dipping coal beds, and so the mining is, I guess, kind of interesting. But then south of the mines, you can see the city of Kampha, which is a big coal exporting location. And then to the northeast in that rectangle, you can see these two plants. They get coal from these nearby mines. And the plants themselves are similar in capacity. They use, though, different combustion technologies. MD1, which is the one to the right in the photograph, it's a CFB plant. And MD2 to the left in the photograph is a PCF plant. And I put just some numbers on the properties of the coal, the ash yield, the calorific values. So you can see it's high ash, but also pretty high heat capacity. And then MD1, the CFB, burns at approximately 900 to 950 degrees Celsius, whereas MD2 is 1290 to 1360 degrees Celsius. And the way that I like to keep track of these as going forward and looking at the results is that MD1, lower temperature, lower number, MD2, lower number, or sorry, higher number, higher temperature. So MD1, lower, MD2, higher. Dr. Kolker and his collaborators, when he was there, collected samples of feed coal from the conveyors going into the plants, and then fly ash and bottom ash from each of these two plants. And that's what I'm going to talk about then going forward. So the CCR material from these two plants have pretty similar major element inorganic chemistry, which you can see in the plot here. These are the major oxides shown on an ash basis, which means that they're normalized to not including the organic carbon content. So we found they have these similar ash yields, as I showed in the previous slide, which are pretty high. And then we also found they really are similar in major element composition, really high aluminum and silicon, greater than 80 weight %, silica plus alumina. They're also low in calcium, less than 2 weight % calcium oxide. And so if we were going to try to use them as supplementary cementitious materials, they'd be classified as class F as opposed to class C, which means that they have that composition. There's some slight differences in the ratios between MD1 and MD2, and that's consistent with feed coals, which you see on the far right of this plot. Again, looking similar to the ashes, which is consistent with the principle that most of the chemistry of CCR is based on the coal that goes in. I guess that's a mass balance kind of approach. Also worth noting in these samples in particular is that they have really low sulfur in both the feed coals and in the CCR materials. And that means that at this CFB plant, at MD1, they add a minimal, if any, amount of limestone as an emissions control. That's different than a lot of CFB plants where they can add like a third of the amount of coal as the mass of limestone added. So it can be big, but here it's not. So when we look at rare earth element concentrations, there's a few things we see. So these are plots of the rare earth element concentrations normalized to average upper continental crust, which we do to make it easier to see. And I have the total rare earth element concentrations listed to the right of each of these plots. So each of these plots has 4 different samples from MD1 on the left in green and MD2 on the right in blue. Going from lightest to darkest, the circles are fly ash, the triangles are bottom ash, the diamonds are feed coal on an ash basis, and the squares are feed coal on a whole coal or total basis. So you can see then that, as we expected, there is rare earth element enrichment in the CCR materials relative to the total feed coal, which are the squares on the bottom. We also see an enrichment relative to upper continental crust. That's 1 on these plots. That's good because it would be kind of a shame to try to refine these if we could try to refine dirt with a higher concentration. That's kind of a simplification, but it's a sign of enrichment that these are more concentrated than average upper continental crust. So another thing that we see is that the relative concentrations of the different rare earth elements are similar in the different fractions, the fly ash, bottom ash, and coals, but then also between MD1 and MD2, which makes sense. They have similar compositions or similar shapes of these plots. They do have a similar geologic origin. They're not from the exact same seam in the exact same mine, but they are from the same general area of a single coal field. So they do have similar compositions. Although the MD1 is about 25% higher in concentration than MD2, that's consistent across the different fractions, including that feed coal. Another thing to note here is that the most enriched relative to upper continental crust rare earth element here is dysprosium, Dy, terbium, just to the left of it, Tb, also relatively enriched. And then cerium, the second one in, is fairly low. And in terms of processing and economics, that's a good sign because having more of those generally more favored rare earth elements relative to cerium, which is often considered excess, that's a good sign in processing, more favorable economically. So those are the rare earth element concentrations. Like the overall bulk element, major element concentrations, they're similar between MD1 and MD2, and they're similar, at least on an ash basis, between the feed coals and the ash or the CCR. So we've seen that the chemical composition is similar, but now we're going to look at the mineralogy. So this plot here shows X-ray diffractograms for the feed coal, the top in purple. It's basically the same, at least visually here, for both MD1 and MD2. So I've just shown one line. And then with MD1 fly ash in green in the middle, MD2 fly ash in dark blue on the bottom. So what this is showing, XRD measures, it shoots X-rays at the mineral sample, and then depending on what crystals, what minerals are present, the X-ray beam is diffracted at different angles, and you get a set of peaks, and each mineral has kind of a diagnostic set of peaks, so you can identify from all of the peaks present what minerals are likely present. Not down to a very small degree, like we actually can't see if there are any rare earth element minerals because the fractions of those would be too small since we're looking at those ppm levels. But for major mineral phases, you can see based on these peaks what's there. So I'm going to go over a few of these minerals just to look at how that changes from the feed coal to the ashes. So if you look at the blue Ks here and here, I marked with checks and X's whether those peaks are present or absent in each of the diffractograms. So looking at the kaolinite, you can see in the feed coal you have those two peaks are very clearly present. But then if you look down in the CCRs, the fly ash from MD1 and MD2, those peaks are gone. And this reflects that kaolinite starts to dehydroxylate and thermally alter around 400 to 600 degrees Celsius. So it's present in the coal, but it's thermally altered to something else in the fly ashes. So then looking at light muscovite, which are sheet silicates or mica minerals represented in red with the eye, you can see clearly here in the feed coal, big peaks, smaller peaks, but definitely still present in the MD1 fly ashes, but then gone, no peaks in the MD2 fly ash. And similar to kaolinite, illite or muscovite starts to thermally break down around 800 to 1,000 degrees Celsius. So you see it present in the unaltered or unheated coal, present in the less heated fly ash, but then not present in the more heated fly ash from the PCF boiler. And then finally, mullite, here in the orange M, is a mineral, an aluminosilicate mineral that forms from the thermal alteration of kaolinite, which again we saw in the coal, but not the ashes. And you can see there's no mullite in the original coal, peak here that you can't see. And then we start to see maybe a little bit of this peak here in the MD1 fly ash, though we don't see those double peaks here. And then by the time we get to the highest temperature, the MD2 fly ash, we do see a distinct peak at both this location and then this double peak here, indicative of the presence of mullite, which forms around 1100 degrees Celsius. So what we see here is a thermal transition going from the feed coal with really minimal heat, and then up to the 900 degrees-ish of MD1, and then the 1300-ish of MD2, and different minerals present with that thermal transition at each or within each. So then another feature that we can see from the X-ray or the XRD pattern, if we look at a different scale here, so this is 15 to 30 degrees 2 theta, whereas that here is 15 to 30, so it's kind of squished up, is we can see these broad humps that are indicative of amorphous content. In this case, it's probably amorphous aluminosilicate glasses. And so what this is where you have heated minerals that are melted, and then they sort of fall within the boiler in little droplets, and they are cooled too quickly to form organized crystal structures. So they don't really have peaks within the X-ray diffractograms. They just have this broad hump. And you can see it sort of here in MD2, it's pretty distinct, whereas in MD1, it's pretty minimal. And then there's too much interference from other stuff in the feed coal. There are other amorphous, organic phases, I guess is how you would describe them. So from these XRD results, what you can see is that similar major element chemistry we mentioned before, but the minerals that are made up of those different elements are distinctly different among these three different locations that have been subjected to different sets of temperatures. Kind of abstract from those diffractograms. So we also have some photomicrographs, pictures taken on the scanning electron microscope that I think illustrate this a little bit more visually. So on the left is MD1, and you can see there's a lot of variation in particle size, but also in particle shape. You know, you see some rounded particles, some flaky particles, some that really don't have much of a shape, all kinds of different morphologies. But then if you look on the right in MD2, the sample from the PCF, it's pretty much all round. You see most of these particles are spheres, and they can be hollow or they can be filled. You can see some kind of hollow structures here. But like I said previously, this is the shape that you get when the minerals melt, form some kind of melt, and then fall and cool quickly, forming these little droplets that are spherical shaped. So this again illustrates that we have, although earlier we determined that they do have pretty similar overall chemistry. Here we can see they have really different morphology, indicating those different mineral phases present that we saw from the XRD results. So we're going to tie together now that chemistry and the morphology. So this is the same image, the background upper image of MD1 from the previous slide, but now it's been scanned with energy dispersive X-ray spectroscopy, or EDS, to identify what elements are present. So then each element or combination of elements has had a color applied so that we can see what particles are made up of what chemistry. Note that gray here is background, so it's the space between the particles. Silica is this kind of olive color here. And then we have aluminosilicates in blue with different other element concentrations, like the inclusion of iron and potassium as different shades of blue. We also have these red iron oxides and purple calcium sulfates that are formed in the CFB boilers, specifically with either that addition of limestone or limestone within the original coal to trap that sulfur dioxide gas in a mineral form, as opposed to it going to a scrubber emissions control. So the calcium sulfates are basically sulfur not forming sulfur dioxide gas that escapes. And then there's some small pieces of residual organic matter coal that's this brown color. So what you can see here is that, you have a number of these different particles in different shapes. The silica tends to be these big chunks or agglomeration of chunks with some of the aluminosilicate solids, but distinct minerals with distinct chemistry, or these clumps of minerals, which can happen as the minerals are heated but don't fully melt, then they start to kind of agglomerate. And then we want to contrast this with MD2, the rounded spherical material. So this is the same picture again as 2 slides ago, now with that similar color scheme applied for the different composition. On again, silica in olive color, aluminosilicates in various shades of blue to green for these calcium-rich ones, red iron oxides, organic materials. So to note here, some of the differences beyond just the shape of the particles, the spheres, are that we see fewer independent, or at least large independent silica particles. They tend to be more trapped in big chunks within these aluminosilicate melt spheres. We also see now these calcium-rich aluminosilicate bubbles or spheres, and fewer of these purple calcium sulfates. And this shows the different fate of calcium when it's not reacting with the sulfur within this higher temperature environment. Then we also see some of these smaller iron oxide particles and larger pieces of residual organic carbon. And just to note, these two, this one and the previous one images, are both on the same scale, where this scale bar is 250 microns, or a quarter millimeter. So pretty tiny. The reason that we care about the morphology and the minerals that are present is that one of the big challenges trying to extract rare earth elements from CCR is that these aluminosilicate glasses, which are more common in coal ash because PCF boilers are a more common type of coal-fired power plant, and generally also larger scale plants. They're really difficult to break down and extract the rare earth elements from. The rare earth elements tend to be trapped within these glasses, and it takes a lot of acids or strong bases, then strong acids, to break these solids down and get the rare earths out into a solution from which they can then be separated by like solvent extraction or ion exchange. And so it's an intense and therefore expensive processing. So finding ways around that would be presumably less expensive and easier. So like I said, that effort does, or how to extract them, does depend on what minerals are present in the CCR, and then what minerals the rare earth elements are contained within. So to look at this a little bit more specifically, we looked at these samples again on the scanning electron microscope with the energy dispersive X-ray spectroscopy, which is a lot easier to say when it's just EDS. But the way that electron backscatter signal works on an SEM is that elements with higher atomic numbers, or like further along the periodic table, those elements are brighter in backscatter. So because the rare earth elements generally have higher atomic numbers, like 50s and 60s for the lanthanides at least, those atomic numbers are a lot higher than like 13 and 14 aluminum and silicon. So when we look just regular backscatter, we see in this image different shades, some brighter, some duller, and that does reflect the composition. So if we change that threshold so that we're not looking at all of these different elements, but just the very brightest ones, we can filter out a lot of that aluminum and silicon and look for just the bright spots. You can't really see in this, but there's a bright spot in this little square here, I can assure you. So then if we scan the sample for just those bright spots, we can then look at them more specifically for their composition with the EDS, which then tells us, again, what those elements are, not just bright, but like yttrium. So if we zoom in on this little square, so this is 1 millimeter scale bar for these two images, and this is 5 microns for that tiny little square there. We see this bright particle here at increased magnification, and then if we hit it with the EDS, then we can get a chemical spectrum, and it's difficult to see the labels here, but what this spectrum shows is that this mineral is rich in yttrium and phosphorus. So we can then infer that it's likely the rare earth element mineral xenotime or yttrium phosphate. So we can scan an area looking at these bright spots, and then we can measure these particles and get an idea of the total area over a specific small area of our thin section sample. And then we can compare that area and the composition of those particles to the overall composition and area that we have from the bulk samples. And we can estimate, and I want to emphasize this is an estimate because some particles are really too small to quantify, what fraction of our total area these rare earth element rich particles account for. So we looked at an area of this sample for cerium and in these bright particles. And what we found is that these distinct independent particles accounted for maybe about 10% of the MD1 fly ash sample and only about 1% of the MD2 fly ash sample. So what this suggests is that more of the rare earth elements in MD1 are likely present in these independent rare earth element rich minerals like xenotime or monazite or zircon, more so in MD1 than in MD2. But also, I said 10% and 1%, and those are overall pretty small. So what that suggests then is that the majority of our rare earth element content in both MD1 and MD2 isn't in these minerals. So based on what we know from previous studies from the literature and then also work that Alan has done previously, is that if the rare earth elements in CCR tend to be dispersed within those aluminosilicate glasses, those little spheres that we saw in the MD2 fly ash. But as you may have noticed, those spheres don't exist in MD1. You can kind of see that here, that the minerals didn't fully melt and form those glasses in MD1 in the CFB with the lower temperature. So the rare earth elements can't be trapped in those. They don't exist. And so what that suggests then is that they are disseminated, so not concentrated, but within other minerals that exist in MD1, again, based on the literature, likely some of those clays. So to kind of back that up again to our power plant technology, the lower temperature of the CFB, we don't get the melting of those rare earth element rich minerals and sort of immobilization within aluminosilicate glasses. But we do see that in the higher temperature of the P2 plant. More of those minerals are likely dispersed within the glasses. And because that glass requires more extensive processing, more acids, more work to extract rare earth elements than clays typically do. There's some ion exchange clays that are rare earth elements deposits in China. Not saying that these materials are exactly like that, but it's a possibility that those technologies might be applicable here. So the lower temperature CFB, CCR might be a more favorable rare earth element feedstock to get those rare earth elements actually out of the solid or separated from each other and from other elements relative to the glassy PCF, CCR. So that's our current research. And just to go back over the high points. So we had these two coal plants that had different boiler technologies. They were burning almost the same feed coal without too much stuff added in, pretty similar. And then the CCR produced by both of these plants had similar bulk chemistry that was reflective of the feed coals. So similar both to the coals that went in, but then also to each other, the two different plants. And they showed rare earth element enrichment relative to both the original coals and to upper continental crust general geology. So those were similarities, but then due to these different operating temperatures of these two different boiler types, we saw different mineralogy within those two different CCRs, which might mean that different extraction technologies could be applied to the PCF CCR versus the CFB CCR. That's a lot of letters, sorry. And so this could be promising for extraction, maybe easier extraction from CFB coal plants, which are common in Vietnam, but also I hear they're somewhat common in South Africa as well. So that's, I guess, something to be followed up on, but our preliminary results, CFB plants, are interesting. So I hope that you're able to find out more about yours. And that's all I have, unless you're curious about references that I've referenced throughout. But thank you for listening, and I guess we have time for questions. Thanks.
We certainly do. Dr. Levitan, thank you for that presentation. With that, thank you everyone for making the time. We'll connect again in a month's time for the next masterclass, which will look at alternative uses of coal, which is really a continuation of the current series. Thank you for your time, Dr. Denise and your colleagues. Thank you and enjoy Wednesday. We'll speak soon.
Thank you very much.